Alright, silly people, here's the situation. We have a probability density um, given by this uh, equation here, and we're meant to find what A is after we normalize it, as well as the expectation value of x, the expectation value of x squared, the standard deviation, and we're meant to also find a graphical representation of it. So, starting with normalizing it, we need to find the integral over all space of the probability density with respect to x, and set it equal to 1, and that'll give us a. So a times the integral from negative infinity to infinity of e to the minus lambda x minus a squared dx equals 1. We're going to do a u substitution. So we're going to have u is equal to x minus a, and so du is just dx. And then this guy becomes just e to the minus lambda u squared du equals 1. And that is a table integral, which I've already pulled up. That evaluates to just square root of pi over lambda. I tried to make it nice and general so it actually looks like a table integral. But yeah, it's the square root of pi over whatever your coefficient is. So that is equal to 1. We can solve for a now as being just root lambda over pi. And so we've normalized the probability function as being square root of lambda over pi times e to the minus lambda x minus a squared. Alright, now we need to find the expectation value of x, which is the integral over all space of x times the probability distribution. So that's going to be from minus infinity to infinity. I'm going to go ahead and plug in the u substitution. So you'll have u plus a, and then this is going to be e to the minus lambda u squared du. So we're actually going to do two different integrals. And I better remember the normalization constant actually. Yeah, it needs normalization of root lambda over pi. When we split this up, we'll have root lambda over pi, integral of u e to the minus lambda u squared over all space, plus a times the same integral that we did before. And so the integral on the right we've already done. The integral on the left is 0, because what you did there is you multiplied your exponent, your Gaussian, by a odd function, which makes it asymmetric around 0. So if you take the integral over all space, the components on the left-hand side of 0 cancel out those on the right-hand side of 0, so you just get 0. And then, so the integral on the right we already did before. We found that it was just pi over lambda under a radical. And so you get that the expectation value is just a. Nice. So now we need to do the expectation value of x squared, which is just going to be the probability density multiplied by x squared and taking the integral of it over all space. I'm going to go ahead and plug in my u substitution and carefully remember the normalization constant. So it'll be the integral over all space of u plus a squared e to the minus lambda u squared du. So we're going to end up doing three integrals now when we expand that square. So you got lambda over pi. You got the integral of u squared e to the minus lambda u squared du. Plus 2a times the integral over all space of u e to the minus lambda eu squared du, plus just a squared times this thing, e to the minus lambda u squared du. All right. The second two integrals we've already done. This one evaluates to 0. The last integral is another table integral, which has the result that I will write down of, we got root pi over 2 times lambda to the 3 halves. That's the solution to that table integral, and then we had just a squared root pi over lambda over here. Okay. Distributing through the normalization factor, you get a root lambda over 2 times root lambda cubed plus a squared. So you get 1 over 2 lambda plus a squared. Cool. So then the standard deviation will be the square root of the squared expectation value minus the expectation value squared. Which is going to be square root of square root of 1 over 2 lambda plus a squared minus a squared. Those a squareds will cancel out and you'll get just 1 over root 2 lambda. Lovely job. Okay, so that's everything that you needed to find the problem analytically taken care of. The problem also asks for you to sketch what the probability density looks like. And so I have actually a Desmos thing open right here. So this is the probability density plotted on Desmos. It's a Gaussian. The peak occurs at 2 times the square root of L over pi, or lambda over pi. So that's where the peak is defined to be. And then the center of the Gaussian is exactly on A, which makes sense because the expectation value was A. So it's most likely to be in the middle. Yeah. There you go.